Rotating electrical machinery is a part of much military equipment. Whether it is a simple blower or a complicated electronic device in a missile, they all depend on the proper functioning of rotating electrical equipment. Two types of motors and generators are commonly in use: alternating current or AC and direct current or DC motors and generators. This film will show the principles governing the operation of DC motors and generators. Basic to the understanding of DC motors and generators is the simple generation of an electromotive force, an EMF. Mechanical energy, the moving of a wire or conductor across a magnetic field by hand in this instance, produces electrical energy. The magnetic field is composed of lines of force. As the conductor cuts these lines, an electromotive force, or EMF, is generated in the conductor. Moving the conductor down through the field makes the needle of a voltmeter deflect one way, which means the EMF has one direction. Moving the conductor up through the field produces the opposite deflection of the needle. The EMF has now changed direction. Moving the conductor back and forth with the field does not make the needle of the voltmeter deflect. There is no EMF because the conductor is not cutting the field. To illustrate the direction of current flow, the conventional symbols will be used. Current flowing in a conductor away from us is represented by a cross, toward us by a dot. However, moving a conductor in and out of the field in this straight reciprocal fashion is awkward and impractical. A simple generator of EMF can also be made by rotating a single turn coil within a stationary magnetic field of two magnets with opposite polarity. The loop now, in effect, becomes two conductors because both the top and bottom sections cut magnetic lines during rotation. Since they cut lines of force of opposite directions as they rotate, EMFs of opposite polarity will be generated in the conductors. In order to have current flow in this circuit, polarities of the two conductors must be opposite. The amount of EMF generated at any instant is determined by three factors: the strength of the magnetic field, that is, the number of lines of force, the length of the conductor cutting the lines of force, and the velocity with which the conductor is turning. We can determine the amount of instantaneous EMF by a simple formula. The instantaneous EMF E equals B, the strength of the field, times L, the length of the conductor cutting lines of force, times V, the velocity of the conductor. An increase in the number of lines of force or the strength of the field increases the instantaneous EMF in the conductor. Increases in the length of the conductor cutting lines also increases the EMF. And finally, the greater the velocity of the conductor, the greater the EMF. This formula assumes conductor motion in a straight line. That is to say, cutting the same number of lines for each increment of its motion. But the conductor in an actual machine is not moving in a straight line, but rotating. When the conductor moves in a rotary path, the number of lines cut varies depending on the position of the conductor. At the top of the field, for instance, no lines are being cut and no EMF is generated. As the conductor keeps turning, the number of lines cut increases, so that at a quarter turn or 90 degrees, the maximum number is being cut and maximum EMF is generated. Again, at 180 degrees, no lines are cut, no EMF. We reach a maximum again at 270 degrees, and finally, again at 360 degrees, no lines are cut. The conductor has rotated 360 mechanical degrees, which correspond in this instance to 360 electrical degrees. Therefore, when the conductor moves in a rotary path, another factor is added to the original formula for the determination of instantaneous EMF. The formula that now applies is instantaneous EMF equals field strength times the length of the conductor times velocity multiplied by sine theta. Theta is the angle formed by the flux line and the motion of the conductor. The number of lines cut and the amount of EMF generated is proportional to the sine of the angle formed by the magnetic lines with the conductor motion. A graph of EMF versus conductor position during one revolution will be a sine wave representing alternating current, or AC. All rotary generators produce AC internally. What you have seen so far is really the theory and operation of a basic AC generator, but our purpose was to explain the principles of operation of a DC generator. To get direct current, we will attach each end of the conductor to a segment of copper, forming a commutator. Now our machine is a DC generator. The commutator rotates with the loop. Stationary contacts, carbon brushes, ride on the commutator segments. They provide a means of connecting a meter or any other load to the generator. The loop of a conductor, wound on a rotor, and the commutator are referred to as the armature. As the loop revolves and the EMF in the conductor reverses polarity, the connections to the load are also reversed, and the current flow will maintain the same direction externally. Represented graphically, the output amplitude still varies. The DC is in the form of pulses. It is a pulsating direct current, or PDC. The pulsation from 0 to maximum, twice for each revolution of the loop, is called ripple. This ripple can be reduced by adding more loops and more commutator segments to the existing armature. 2 loops at right angles connected to 4 commutator segments provide 2 outputs instead of 1. These outputs are 90 degrees displaced or apart, which combine to smooth the DC output. However, even with 2 loops and 4 commutator segments, the rectified curve is still somewhat irregular. By adding magnets, we increase the number of fields cut by the armature. As we increase the number of loops and commutator segments, the variation between maximum and minimum value decreases. This, in effect, tends to flatten the DC output. Practical DC generator armatures have a great many loops wound on a rotor. The field is composed of many electromagnets. Together, these factors tend to create an almost pure DC output. An important problem in the design of generators is the prevention of sparking between the commutator and the brush assembly. The prevention of sparking depends on the position of the brushes. This line through points of zero generated EMF is called the neutral plane. Placing the brushes in this neutral plane reduces the tendency for sparking between brushes and commutator, because during the time a brush is touching both commutator segments, there is no difference in potential between these segments. Theoretically, no sparking should occur at the commutator brushes when they are placed in this position. But the current flowing in the armature loops or coils sets up a magnetic field of its own. This magnetic field interacts with the main magnetic field and distorts it. The distortion causes a shift in the neutral plane and sparking at the brushes. The effect is called armature reaction. Sparking may cause severe interference in nearby electronic equipment. There are two ways of maintaining the neutral plane in its correct position and thus avoiding sparking. It may be done by the adjustment of the brush position. The brushes are adjusted to lie in the adjusted neutral plane. The other way of maintaining the neutral plane is by adding interpoles to the generator field. These interpoles are small magnets placed between the poles of the main field magnets. The interpole fields oppose the fields created by armature reaction. The neutral plane is moved back toward the correct position. In addition, to further counteract armature reaction, windings called compensating windings are sometimes placed in the main pole faces. The current in these windings is armature current flowing in opposite direction to the current in the armature conductors. Magnetic fields in DC generators may be produced by electromagnets or permanent magnets. Permanent magnets are used in relatively small devices like a field telephone ringing generator. In larger generators, the field is created by electromagnets. The field winding used in this DC generator can be represented by a symbol. The symbol is that of an iron core inductor. Current to excite the field windings can be supplied from an external source. In that case, the generator is classified as separately excited. A small part of the generator's own output can also do the exciting. In that case, it will be a self-excited generator. Self-excited generators must be initially magnetized. The residual magnetism in the core of a field winding provides enough magnetism to begin generator action. The field coil winding may be connected in several ways. This is a series wound generator, which means the field coil is in series with the armature. Because of this series arrangement, it has poor voltage regulation. The reason for this can be demonstrated in the following manner. Additional load will cause more current to flow in the field coil. Increase in field strength increases voltage. Increase in voltage causes more current to flow. This continuing action stops only when the core is saturated. When the load is increased, the voltage will increase. When the load decreases, voltage will decrease. Voltage regulation in the series wound generator, therefore, is very poor. When instead of in series, the field winding is connected in parallel with the armature and the load, we have a shunt wound generator. Now the field current is independent of the load current. Therefore, an increase in armature current will not cause an increase in the voltage output. Voltage regulation here is greatly improved. In shunt wound generators, therefore, changing load causes relatively small change in voltage output. By changing the armature winding, a compound wound generator results, which combines the best features of both types, the series and the shunt wound generator. When windings are arranged so that magnetic fields oppose each other, it becomes in effect a series generator. This is used only where constant current is the prime requirement, such as in arc welding. By changing the magnetic polarity of one of the field windings aid one another. As a result, this compound wound generator has good voltage and fair current regulation. A graphic representation of generator output characteristics with terminal voltage plotted vertically and armature current horizontally would look something like this. As we have seen, in the output of the series wound generator, voltage regulation is very poor. In parallel or shunt wound generators, the voltage regulation is fairly good, but current regulation is poor. Compound wound generators offer a flat compounded output that is normally most desirable. It combines the good features of both the shunt and series wound generators and provides stable voltage output under changing loads. As we have seen in our analysis of the DC generator, its primary function is the conversion of mechanical energy to electrical energy. If we now reverse the procedure and connect an electrical power source to the generator, we have a DC motor instead of a DC generator. Motor action can be illustrated by attaching a power source to a conductor which is inside a magnetic field. The electric current creates polarity in the conductor. The south pole of the magnet attracts the north pole of the conductor and repels the south pole. The north pole of the magnet attracts the south pole of the conductor and repels the north pole. This creates movement depending on the direction of the steady magnetic field. The movement